Well, good morning. I'm Chris Lindahl from Cray. I want to start by, there was a great question this morning about whether or not we were seeing a fork in the architectures from one type of computing, or traditional HPC simulation, and big data computing. And at Cray, we don't think that we're seeing a divergence there, but we are seeing it at the microarchitecture level, perhaps. So as we see these microarchitectures diverge, trying to eke out the most performance and efficiency out of those, we're going to need an adaptive system and a flexible network and a common and extensible software stack, really, to bring those together. And with those things, we can drive convergence to one resource. And it's that convergence that's disruptive and changes the way that people will do business. So we've been saying this for a couple of years and presenting this as our vision. Today, I want to use a couple of customer cases and use examples to give a view of where we are in that, realizing that vision. So I want to start with Professor Wendy Tam Cho at University of Illinois and NCSA. And what she's done is she leads a group of people who are attacking gerrymandering and and drawing the districts for elections politically. And years ago, she came up with this concept of using computers to analyze demographic data, deeply analyze demographic data, to draw fair maps and use those fair maps to compare them to what's being proposed and be able to judge that proposed map based on what would be considered fair maps. Well, previously, you could only get to about 10,000 maps, and it wasn't statistically significant enough to make a compelling argument. Well, with Blue Water, she's now able to do billions of maps. And they're able to take that and analyze a proposed map to determine if it's a fair map or if it's been drawn politically. And they're using this as part of planning to drive behavior, as part of litigation, and even to avoid accidents. Another example is a little bit more from our traditional simulation type thing, workloads, where NOAA and NCAR have developed the new national water model. So in this case, they used to have less than 4,000 sensor points, observation points, and they would generate their forecast data. Now they're able to use nearly 8,000 observation points and generate forecast points for more than 2.7 million points. And they're able to do that every hour to determine water rates and whether they're rising or falling. So this is a little bit more of a blending where you see both workloads operating on the same type of a system. I want to use one final example, and that's with Petroleum Geoservices. And they're an innovative company that does 3D seismic imaging. And one of the things that they've been looking at is how they can streamline their process. So in this is an example of a FWI code, and it's a multivariate optimization problem in which you would run the code, observe a residual, make some decisions, make some tweaks, run it again, and continue that to iterate on that loop. And if you look in the top right, that's the source data. That's what we're looking for in that problem. And conventionally, through that iterative process, with that overburdened resources, Dr. Go said, of an expert making a decision on the next thing to try to get better. After a few iterations, you can get something like that middle picture that makes it look like you're able to start seeing, yeah, we're getting a good sense of what's underneath the water there and where we can take things. Well, this still requires a lot of expert analysis and intervention. And PGS decided to go to Rice University and ask for some help in creating a machine learning variant that looked at how to address that next steerable variation quadrant. And taking that and running it back as part of their workflow, they're able to do what you see on the bottom. Again, many iterations, some of them not so great perhaps. But in the end, they're able to show better results faster with less intervention and requirements from their experts, freeing their experts to work on other things. All this on one system, and it's that interaction between the workloads where we're currently just now getting to that's going to be really exciting, where the output of one can dramatically influence the other immediately.